All right, so let's begin our review of Unit 13, or optics, geometric optics. So first about reflection. So light rays we draw as like kind of pointing in the direction that the wave is moving. When it encounters a surface, the light reflects at the same angle relative to the normal. So for example, if a light comes in like this way, remember that if it comes in this way, it's going to reflect at the same angle. These two are both the same angle relative to the normal of the surface. Now, a couple of definitional terms. A diffuse reflection is when it's on a rough surface where like it's really jagged. So what ends up happening is when the light hits it, it bounces at different angles because the surface is like kind of rough. But if it's a smooth surface, nice and polished, you get a specular reflection because then all the light waves that come reflect at the same angle in the same direction, basically. That's just definitional stuff. Nothing computational on that side. All right, refraction is when it passes through a different medium, and this is where it gets a little bit more complicated. A couple of things change, and a lot of this is covered also in the waves unit in the following unit. So the speed of light changes, right? And the speed of light, c is 3 times 10 to the 8, right? And the speed of light will change by a factor n. We call it the index of refraction. The frequency of the light doesn't change, but the wavelength will change. And light will bend according to Snell's law by this. Light will reflect at the same angle relative to the normal, just like the reflection. So there might be a refracted wave and a reflected wave. When light moves in a slower medium, that means a higher index of refraction, then the light will bend more toward the normal. And when it moves in a faster medium, goes faster, then the light will bend away from the normal. So for example, if this is where the has a higher index of refraction, then if the light comes in, it's going to bend more towards the normal, and if this were faster, it would bend more. It would have a bigger angle relative to the normal. Now, the total internal reflection occurs when the refracted angle ends up being 90 degrees. In other words, if you go from a slow to a fast, right, you're going to come in here, and you're going to bend away from the normal. And if you bend away from the normal enough that you're exactly horizontal, then we say the light doesn't actually pass into this surface, right? Any refraction occurs and stays within the medium, and so that's called total internal refraction when that occurs. Ray tracing basics. Remember, with optics, with lenses and mirrors and stuff, we draw. We drew ray tracing. Comes from an object towards a mirror lens. Mirrors use reflection rules. Lenses use refraction rules. So lenses will refract, mirrors will reflect. Couple of standard things. A real image is where the light travels through the point in space. That means when the light converges, it converges at that location for the image to form. A virtual image is that the light appears to come from that location. It doesn't actually come from there, but your eye imagines all light travels in a straight line, and so it will appear as though it came from a single point in space. All right, and so we'll talk about that when we do some examples. And where the light converges is the location of the image. That's where it is in focus. Okay, for mirrors, we operate by reflection, whereas lenses operate by refraction. Concave mirrors, let's look at the ray tracing. So concave mirror looks like this. It's spherical, it's circular, and we have something we call the focal length, right? This is the focal length. So there are 3 rays that you can draw. Any light ray that goes horizontal to that principal axis, which is where the center line is, anything horizontal will reflect towards the focal length. Anything that goes to the center will just reflect with the same angle, because here the surface is this way, so it's perpendicular. And anything that passes through the focal length will then reflect horizontally. And where all 3 rays converge is where the image will form here. Okay, so convex mirrors, that's where you're bouncing on the outer edge of this. What happens is the reflection's a lot more complicated, and it always makes a virtual. So this is a real image here because the light actually converges at this point. For a convex mirror, you do a horizontal ray, and it bounces away. It reflects away from the focal length. If you draw a line like this, it's going to reflect away from the focal length. Anything that bounces towards the focal length will reflect horizontal, and anything that goes towards the principal axis through the center will just reflect at the same angle. Okay, so those are the 3 ways we draw. And you see here, if you look at this blue ray, this yellow ray, this red ray, they don't intersect over here. However, if you backtrace them, if you say well, imagine they came back from a point, then it looks like they intersect here. Now, this is a virtual image because the light rays don't actually pass through here. The solid lines are where the light actually travels. The virtual image is where it looks like the light appears to be coming from, right? If it did travel from a single location at a straight line, right? So that's the distinction between the real and the virtual image here. And so the virtual image will appear on this side of the mirror. Okay. For lenses have similar rules. They have focal length still, right? This is the focal length on both sides. For a converging lens, by the way, looks like this, right? So converging lens looks like this. And this is for thin lenses. Light rays that go horizontal to the axis, number 1 here, will refract towards the focal point. Any light rays that goes to the center, it's shaped in such a way that it will go unchanged. And light rays that go through the focal length on the other side will then appear to go horizontal. And where they intersect is where the object occurs. For a diverging lens, right, diverging lens looks like this instead. So any horizontal line that goes here will bend away, but it will appear to bend away from the focal point on this side. Anything that goes towards the focal length on this side will bend horizontal, and anything that goes through the center of the lens will then just go through unchanged. And for a diverging lens, it always will create a virtual image because they don't converge on this side, like the real light rays don't, but it looks like they converge at this point over here, and that's where the image would be. Okay, we also have mirror lens equation. This is the analytical way. So there's ray tracing where you can graphically do it, but then there's equations we can use. Mirror lens equation is 1 over SI plus 1 over SO equals 1 over F. And the magnification is the height of the image divided by the height of the object, or its negative object distance, image location over the object location. So when you're using, the key thing is this equation. The sign convention you want to use here is for a diverging lens or convex mirrors, the focal length is negative. For a converging lens or concave mirrors, the focal length is positive. So keep that in mind. So for converging and concave mirrors, which is what they're kind of bending towards the focal length, it's a positive focal length. The image, if you solve for SI and it's negative, then you get a virtual image. If you get SI is positive, then you get a real image. And S0, where the location of the object is always positive. Okay, so that's kind of the sign convention we use, and then we can use that to calculate the location of the image. And once you know the location of the image, then you can actually calculate the magnification. This is a table of behaviors. I would honestly not necessarily memorize this, but this is sometimes helpful for people to see that a converging lens can sometimes have a virtual image if the object is located less than the focal length. But a diverging lens always has a virtual image, and then you can kind of see sometimes it'll be bigger, smaller, sometimes it'll be inverted. Inverted will be if the magnification ends up being like negative, right? Like if it's negative, then it means it's inverted. Okay. So let's take a look at a few examples. Student places a lens 40 centimeters from object observed an enlarged image on the screen on the opposite side of the lens, which could be a type of lens and the focal length of the lens. Okay, so if we appeared on the other side, it's got to be a converging lens, right? Because remember, diverging lens, the lines are going to go bending away. So it's going to definitely be a converging lens. And it's an enlarged image on the opposite side. So let's see which one is going to make it enlarged, right? By using our, use this equation. So 40 centimeters is where the object is located. That's 1 over 40. Okay. And we want to know the focal length, and we got to get, we're really narrowing between here. Well, let's do 1 over 30, and let's see 1 over SI. So if we do that for part C, if we solve for SI, you do 1 divided by 30 minus 1 divided by 40, and then you do 1 divided by that. You get SI is 120, right? And so that'll give you a larger image. It's also not negative, because like we said in the sign convention, it's real image. We want a real image. However, what's happened if we use the 51, 1 over 40, and the focal length is 1 over 50. Then if I solve for SI over here, I get 1 divided by 50 minus 1 divided by 40, and then 1 divided by that. I get a negative number, negative 200. And the issue with this one is that because it's negative, it's a virtual images, so the object doesn't appear on the other side, right? So that's why it's a converging lens with 30 centimeters. All right, diver is swimming underwater in a pool filled with water. An observer is standing on the edge of the pool as shown. Will the observer always be able to see the diver no matter where the diver is in the pool? Why or why not? Um, so it's always about like how the light refracts, right? So for example, we got to think about how the light's gonna travel from the diver to this guy's eyes, right? So like this guy's eye, he's not gonna see the diver here because if we look at it, it's gonna bend more towards the normal. That means if he looks over here, then it will bend this way, like this, right? And so that's the one thing we got to keep in mind. That's gonna because it's gonna bend more towards the normal due to that refraction that's going on there. So then the question is it always possible to find a light ray no matter where he goes? Like if you look at the observer, if he looks over here, right, sees this edge, well, let's get like something over here. It's going to bend towards the normal, but it's still going to be able to hit somewhere in here. And if he draws over here, again, it's going to bend more towards the normal, so it's going to go almost vertical. It won't go quite vertical because there'll always be some angle. So yes, pretty much there's always a spot that no matter how he looks at it bends, that the light ray will hit. Now, if this were like opposite, like if this were air instead down here, or this was like a smaller index of refraction, we were bending away, then there would be some that the light wouldn't hit the diver and come back. Or it's actually reverse direction, right? So it's going this way, but it's the same idea, right? So that's why, let's look at the answers. Yes, because there'll always be a light ray originating from the diver that will refract toward the observer and reach the observer. So that one seems good. Yes, because every position diver, there's a straight line path connecting the diver and observer. That doesn't matter, right? Because the light's going to refract. No, because light passing from a medium with high index of refraction to low index of refraction will always total reflection. Now, it has to be at a certain angle, so it's not always going to totally reflect. No, because some some of the light rays from the diver will totally reflect at the water-air boundary. It's possible that there's going to be some that totally reflect, but that's when you go from let me think about let's think about why would D. No, because the light rays from the diver is going to a lower index of refraction. Well, no, that's actually how you get reflection. So I think it's because from the diver will totally reflect at the water-air boundary. I think part D we don't know without knowing the relative index of refractions. I think that's the issue there. You might need to know some external knowledge about it, about how the critical angle tends to work. But let me think. Yeah, I'm going to say D is also a possible answer. I think College Board marked A as the correct answer. It's possible water-air boundary without specific numbers and specific angles and dimensions and things like that. It's impossible to say. It's possible that there will be light that does totally does reflect totally inside the boundary there. Oh, sorry, I'm mistaken. So D, the total internal reflection occurs from the diver's perspective, not the observer's perspective here. That's the issue. Is that like and this sometimes happens if you go into a pool, look under the water, you'll see like it's really hard to see outside of here because sometimes you'll just see a reflection of what's down here because all the light will just reflect and back into here. But from the observer's point of view, there's always going to be a refracted line that goes through there. Okay, so the total internal reflection is really for the diver's perspective, not the observer there. All right, we have a converging lens with focal length f is used to project an image of an object placed at a distance d0 from the lens. Okay, a screen is placed on the other side of the lens and the image is found to be focused. So we have a converging lens that's focused. This distance here is, let's see, object placed distance. Okay, so the object is placed d0 here. So this distance here is d0. The object is now moved closer to the lens, so it's exactly one focal length from the lens. So let's say the focal length is here. Will the image on the screen move closer to the lens, farther from the lens? Actually, let's say this d0 is greater than f. I think we need to specify that. So we need to understand how is this going to do, and where is the image going to be, right? So we have this equation: 1 over si plus 1 over so equals 1 over f, right? And so the image. We want to infer something about the size of the image, the location of the image. So 1 over si becomes 1 over f minus 1 over so. Now, if SO is bigger than F, then this number here is going to be smaller than this guy. So this is going to be a positive quantity. So it's going to be a real image, right? It's going to be a real image on the other side. And but what happens is as the SO approaches F, then these two will add to 0. So 1 over SI will eventually go to 0, and that means SI goes to infinity. That means the image is going to vanish, right? The image is not going to, will the image move closer to the, on the screen, move closer to the lens, further from the lens, or disappear entirely? It's going to disappear because when the object is located exactly at the focal length, at the focal point, the light never converges to form an image. And so here we're going to do this 1 over di plus 1 over do equals 1 over f. So 1 over di is 1 over f minus 1 over do. So we just want to just make sure we understand how to use this equation. So di, you can just do 1 over on both sides. Whatever you do to the left side, as long as you do the right side, is fine. You do 1 over on both sides, you'll get 1 over this. So you can leave it like that. If you just, your sensibility doesn't like fractions within fractions, you can write this as d0f over f minus d0. I think, well, actually, so let me show you how you get there. You would want to add these two fractions together by common denominator. So if you do 1 over f minus 1 over do, you'll kind of, common denominator is going to be d0f, right? And so this side you're going to multiply by f over f, because that's like multiplying by 1. And so then you get d0 minus f on the numerator over d0f. And then if you flip it, you'll get d0f over d0 minus f. Either way is an acceptable answer for that one. I would leave it like this, though, personally. Does your expression in part B support your claim in part A? Justify why or why not? Yes, because the denominator goes to 0. So di approaches 1 over 0, which approaches infinity. Okay, so something like that. I would use words for that. I'm just not writing out the words just for brevity sakes and just doing the review, but you should write out some words there for that part. Okay, cool. Student places a laser pointer to shine a light onto a screen located at distance L plus D away. So here's L, here's D, okay? They then place a transparent material of thickness D with index of refraction N greater than 1 between the laser pointer and the screen. So here's some material. The student notices that the laser pointer is now hitting a screen at a different location. The light from the laser pointer enters the transparent material at an angle theta. This should have been not theta 1, but just theta. Explain if the spot on the laser pointer on the screen is above, below, or at the same location as it was before the transparent material was placed. Justify your answer. So the light, it was hitting this location. But now that we're refracting, right, and it's a thicker material, we're going to bend more towards the normal. And then we're going to bend away from the normal and be parallel to this line because we're going to come in at the same angle. And so it's going to end up lower, right? So it's going to be below. Because refracting in a greater index of refraction material will bend the light downward or towards the normal. And end up below the original spot. Okay, so something like that. Now let's derive an expression for the new spot of the laser pointer relative to the original spot. Do it in terms of theta, d, l, and... Okay, so here's what you got to think about on this one when you're doing this. Is that, remember that it's always... And this is air. So air has an index of refraction of about equal to 1. So when we're using Snell's law, let's talk about this first interface. We're going to bend more towards this normal here. So this is 1. So this would be sine theta equals whatever n is sine of theta 2. Right? So this would be theta 2. And then it's going to travel again by going at the same angle here, theta. Because once it gets back to air, like this is going to equal just again 1 sine of theta 3, but then these two angles will be the same because this is the same material here. So really what we're looking for is we're looking for this vertical distance, and so we have to think about like, oh, we need to think about because these two are going to be parallel, all that matters is this vertical distance, right? So we want to use right triangles. So we always want to think about like, oh, what's that distance for that right triangle, this vertical distance here, versus say, this is a lot of geometry when we do optics, right? Versus this right triangle here and finding this distance. This distance, this big green distance for this one, like this original distance, like this triangle that's going to move, is going to be, well, you know, this side is D. Okay, so tangent of theta is going to give you opposite over adjacent. So this is going to be D tangent of theta. Okay, and then this distance here, now that we bend it at a new angle, is going to be D tangent of theta 2, the new angle here. And so then the difference in the distances is going to be D tan theta minus D tan theta 2. Okay? But here we have a relationship, because we can't do it in terms of theta 2. We can say, oh, well, we know sine of theta 2 is equal to sine theta over n. So you can say theta 2 is inverse sine of sine theta over n. You could do some right triangle stuff if you wanted to, but I think this would be fine. And so tangent of theta 2 is going to be tangent of that. I think this would be fine. If you wanted to get fancy and convert this, so this would be d and then tan theta minus tan of sine inverse. If you wanted to get fancy, you could maybe show how to do a conversion from knowing the sine of an angle to the tangent, right? And that's where this is from trigonometry. Again, this is completely optional. You could say, well, this is theta 2. I know sine of theta 2 is opposite, so we just call it sine theta over hypotenuse. Well, yeah, like this, opposite over hypotenuse. And so then this side is square root of n squared minus sine squared theta. And so you could say tan of theta 2. If you wanted to replace this whole thing, you could say tangent of theta 2 is opposite over adjacent sine theta over the square root of n squared minus sine squared theta. So you could replace that in for this part here if you wanted to. It's not necessary to solve to that extent, but you could if you were comfortable doing that trig conversion from pre-calculus. Okay, notice it didn't depend on L. Yeah, and we used the only variables that we're allowed to use. Suppose the transparent material is placed with a different material that has an even greater index of refraction. Justify if the new spot location will be higher or lower. So if we have a greater index of refraction, right, it's going to bend even more downward. So it's going to bend downwards even more. So it's going to be even lower. So it'll be even lower, because a higher n will result in a higher bend or smaller refracted angle. So it will hit even lower. Okay. And that's that.